Right, hey everyone. So Wise started out as a monolithic application, a single deployable unit. As Wise got more complex and some problems started to surface, it adopted the microservices architecture, consisting of loosely coupled microservices, each with its own database. So today, we will look into why this architecture shift happened in Wise and what are the main patterns that helped us through this evolution, through this architectural shift and organizational shift as well. So I'm an engineering lead at Wise, leading a team in our treasury squad. We are responsible for financial risk management through controlling how customers use our product. I've been with Wise for 3 years, so I haven't actually witnessed the transition, the initial transition from monolithic architecture to microservices. When I joined, it was already microservices. But I talked to a lot of people in the company, and I collected some good insights that I can share with you now. So, if you don't know Wise, let me introduce you to Wise. Wise is a financial services company focusing on helping you managing your money internationally. We support more than 160 countries and more than 40 currencies using the Wise account. Our main values are instant, convenient, transparent, and eventually free. We have 3 main products: the Wise account, which is an online account that lets you manage your money internationally. With the Wise account, you can spend abroad, you can receive money in different currencies, and you can pay or you can spend abroad from your Wise card. Wise Business is a very similar multi-currency account, but for businesses. Business customers can use it to pay invoices, buy inventory, and handle payroll internationally in more than 70 countries. Wise platform is Wise, but for banks, large businesses, and enterprises. It's basically a market-leading global payment infrastructure that helps our partners offer world-leading FX products. All right, so now the more interesting stuff. Wise's evolution. So our evolution from monolithic architecture to microservices. We will first look into this transition and why it was triggered in Wise, and what's the kind of Wise-specific context to it. But as I said before, I wasn't around, but I collected this information from a lot of people in Wise who influenced these decisions. So let's look at the timeline. So as I said, Wise started out as a monolithic application in a self-hosted physical data center. It was a small, simple application, so it made sense to do this. And the monolithic architecture provided us with a lot of benefits. It was simple to deploy. It was easy to make radical changes to the application. It was straightforward to test end-to-end. It was straightforward to develop for developers. And it was easy to scale. We could run multiple instances of the application behind the load balancer easily. But by 2017, quite a few problems started to surface. The main problem was our CPU utilization in our monolithic database. It was 50+%, and this is the average, not a spike. So we needed to reduce the CPU utilization of our database to less than 10%, including spikes, to avoid slowness, to avoid outages, and to make the database stable. At the time, actually, there are some anecdotes about this in Wise. So at the time, when there was a database maintenance window, that meant that Wise was down, which was kind of like every Monday of each month. So we also needed to solve this problem. Also, developing new features was quite cumbersome, because the transfer creation process was very complex, overly complicated. Also, our public APIs calls were not really performant, and it timed out many times for heavy users. So in 2017, we already started the extraction of some of our fundamental services, like the transfer or the quote services that are responsible for our transfer lifecycle. But these services still access the master database in the monolith. So we only extracted the code, but not the data. Also at this time, we didn't have a dedicated platform engineering team. No one actually full-time focused on developer productivity and delivery tooling. And also engineers kind of juggled work between product and platform work. So in 2018, our CTO started a company-wide initiative to increase the reliability and scalability of our platform and increase the speed of provisioning infrastructure and services. This initiative lasted from 4 to 6 quarters, or actually maybe even a bit more. And it included some major organizational changes as well, including forming teams around the ownership of these foundational services, as well as platform and delivery tooling. So a major effort went into the modularization of the monolithic application. We extracted services responsible for managing account details and profiles. And we extracted not only the code, but the data into a database per service. There was also a focus in building delivery tooling to increase developer productivity. So we automated the provisioning of services. Our goal was to reduce the time it takes to provision a service to less than a day at the time. And also to allow anyone to bring up on-demand staging environments for multi-service testing, including in-house developers and partners. We also started providing out-of-the-box observability for our developers, including logging, tracing, monitoring dashboards, and alerting. Also in 2018, we started adopting Kubernetes and service discovery via sidecar proxy. And we started introducing async communication to our architecture through Kafka. The reason we started introducing async communication because we wanted to bring down the API response time to less than 2 seconds in 99% of the time. And the reason our transfer creation API response was so slow is because there was a list of post actions that got executed after the actual transfer creation. But these post actions were not necessary to actually return or give a response in this public-facing transfer creation API. So we then created, or that these post actions were migrated to Kafka listeners, and they were executed asynchronously rather than synchronously. So this shift actually led to a 30% improvement in average transaction times, and it moved 45% of our transactions within the less than 1 second execution range. And another note about 2018, very influential year, we started the move to the public cloud, AWS namely, and there was an active push for new services and existing services to be provisioned on AWS. So by 2019, we achieved full extraction and modularization of our foundational services, including the data. So we then hosted the data in a database per service. And this full modularization allowed us to serve our customers even when our monolithic database was down. We also introduced standardized libraries that implemented common patterns across services. So now, fast forwarding to now, Wise is running more than 700 microservices, and engineers are able to provision new services instantly. So when I talk to people in the company who witnessed this evolution, they highlighted a couple of important patterns that they think were quite influential in this transition. One of these is domain-driven design, which is not very much a pattern, but more like a framework. The other one is the Saga pattern, event sourcing, and the transactional outbox pattern. So we will look at these one by one, look at the drawbacks and benefits of each. Of course, a note here that none of these are silver bullets. Just like the microservices architecture, all of them have benefits and drawbacks, and they made sense for us in the Wise context. So domain-driven design is a framework that helps you refactor your monolithic application into microservices in an incremental manner. It organizes microservices around business concerns, not technical concerns. So Wise used domain-driven design in the beginning to define these foundational boundaries for our initial services that we extracted from the monolith. There are a couple of principles that domain-driven design follows. One of them is loose coupling. Loose coupling allows you to change your service without changing any downstream services. So you can achieve this by defining clear API contracts between your services. Another one is cohesion, which requires a service to have a very well-defined purpose, such as managing user account details or processing payments. And the third one is domain expertise. Domain-driven design requires domain experts. So that's why it is recommended to do the extraction incrementally rather than extracting very small domains, because there needs to be a domain expertise built up. And that's why Wise formed teams of people who have been around for a long time and who understood these foundational large domains that we initially extracted deeply. So in Wise's case, we identified quote, transfer, profile, and account details as the initial bounded contexts for modularization. So migrating data-heavy domains is non-trivial. So first we migrated the business logic, the code, and then we eventually migrated the data as well into a database per service. But once you migrate your data into database per service, you are facing a new challenge called distributed transactions. So in a monolithic application, your database guarantees an atomic view of the data, or atomicity of your transactions. That means that you always have a consistent view of the data. In distributed transactions, there is a challenge of maintaining data consistency across services. If any one transaction fails, a local transaction is a service, in a service, then data must be reconciled and rolled back. The previous steps needed to be rolled back in other services that are kind of dependent on this chain. If the rollback doesn't happen, then you have an inconsistent view of the data in your microservices architecture. So the saga pattern addresses this issue, and we will look into the saga pattern next. I'm going to skip this slide. All right, so the saga pattern provides a way to coordinate distributed transactions across services, including error handling. A saga is basically a chain of local transactions that get executed in different services. Each transaction updates the local database and then publishes an event that triggers the next transaction in another service. If a transaction fails in this chain, then the service where the transaction failed publishes an event that triggers a rollback of events in each of the upstream services. So there are two ways to coordinate this chain of events. One of them is called choreography, and the other one is orchestration. In case of choreography, each transaction publishes a domain event that triggers the next transaction in another service. This is kind of like a decentralized approach. And then in case of orchestration, there is a central orchestrator that tells the participants which local transaction to execute. In Wise, we utilize choreography because we find it a more flexible and scalable solution for our needs. So what are the benefits of the saga pattern? It enables you to maintain data consistency across services and also roll back transactions if necessary. And then the drawbacks. So programming the saga pattern is quite complex. Developers need to design multiple events for successful and unsuccessful transactions. All right, another influential pattern in Wise is event sourcing. Event sourcing is a way to persist aggregates as a sequence of events, and each event represents a state change for an aggregate. So an aggregate is a pattern that was introduced by domain-driven design, and it's basically a collection of domain objects that can be treated as a unit, and they belong to the same kind of business domain. It defines a clear boundary and can be treated as one. So, traditionally, in services, we would store an object, as here you see on that side, as a row in the database, and if we would update an object, let's say in this case a transfer, then let's say we would update the status of a transfer from new to pending, we would store the latest state of this object in the database. The previous state is lost, or we would need to implement audit logging to have the history of changes to these objects. So event sourcing is addressing this issue by storing this aggregate as a series of events, you can see on the other side, and which represent the state changes. So we store these events in an event store, which can be a hybrid of a database table and an event queue. And an application using event sourcing would construct the latest state of an object, in this case, transfer 1, by replaying these events. We can use snapshotting to kind of save some state at the time of these events, to reduce the number of these objects, to reduce the number of events to be replayed by the application to get the latest state of these events. So in Wise's case, having the history of events to what happened to certain domain objects is very essential as a financial services company. And this way, we can automate this process and not rely on developers to actually implement audit logging every time. All right, so the benefits of this pattern is that it preserves the history of changes of aggregates. Therefore, it doesn't require additional implementation of audit logging. And then, as I said, automatic publishing of events can be implemented that guarantees that there is a reliable publishing of domain events every time when a domain object was updated. And then the drawbacks. So if there's a new version of an event, then an application needs to account for that new version when replaying the events and reconstructing the current state of a domain object. Also, deleting data in an environment like this is more complex than just this traditional object-oriented domain model. All right. The last pattern we are going to look at is the transactional outbox. So in distributed transactions, we need to make sure that an event is published if a transaction was successful to trigger the next transaction in another service in the chain. So this is difficult because a service can unexpectedly go down after successfully executing a transaction, but before publishing the event. So this transactional outbox pattern addresses this issue. The solution is for the service to insert an event into a table called message outbox in the same transaction that it uses to update the domain object. So in this case, a transfer in the transfer table. Here, in this case, the database guarantees that if a transfer is a database transaction guarantees that if a transfer is updated in the transfers table, then there is also a message inserted into the message outbox table. And then there is a separate process called the message relay that then publishes messages from the message outbox table. So the message relay process polls this outbox table by querying it, and then once it's queried the rows, it publishes them to the message broker and then deletes the published messages. So this can obviously introduce duplicates, but it guarantees that there is at least one message published for each update in the transfer table. So at Wise, we have a common platform library that we use that implements this pattern, and all of our services that actually use Kafka use this library to publish messages. All right, so the benefits of this pattern is that it guarantees that events are sent only when a database transaction was successful. And also, it preserves the order of events. So the order of events is the same as the order of updates in the database. So using a database table and polling for the message outbox can have some scalability issues. So in a small scale, it works very well. But in larger scales, it can get slow and also expensive. Also, developers need to keep in mind that they need to insert a new event to the message outbox table every time they have updated a domain object in some other tables. This can be error-prone because we rely on developers. And also, as I mentioned before, this solution can publish duplicate events. Since the message relay process can crash between reading the events from the message outbox table and publishing them to Kafka. And when it crashes, it crashes before actually committing that it published the events. That's why it can, when it restarts, it doesn't have a record of those events being published, so it will republish them. So consumers of these queues will need to account for duplicate events. All right, so in this talk, we looked at 4 patterns that helped Wise scale its microservices architecture and also migrate from a monolithic architecture to microservices architecture. It was the domain-driven design framework that allowed us to deconstruct our monolith into microservices. Also the Saga pattern that helped us manage distributed transactions across services and maintain data consistency. Event sourcing to define domain entities as a series of events that represent state changes to the domain entities. And the transactional outbox pattern that guarantees publishing events when a domain entity in the database is updated. All right, so that's it. Thanks, everyone. Hope you learned something.
That was a nice talk. Thank you. Thank you for all those insights. I'm actually curious. You said that you split the services into like microservices, or like the whole thing into microservices, and each one has its own database. Mm-hmm. So how you deal with that you now have this data cluttered around if you need to aggregate the data? Are you just going to fetch it from everywhere? How you deal with it?
Yeah, so we do have data available in Kafka queues. So we don't directly reach out to services to kind of get data. We use async communication most of the time between services. And if a service needs to know about some profile state updates, then it just consumes the data from the profile topic and reconstructs the state of each profile.
But for instance, if there is an API call and it needs to be served, the API service then also reads it from Kafka?
No, so obviously there are some REST API calls that we serve, like specifically our public API calls. But what we aim for is to put most of the actions that are not necessary to respond into async queues. So I guess, here there is a decision point, and we make the appropriate decision every time. Like, do we wait for an async response from all the downstream services? Is that necessary? And we always look at this case by case and then see whether we can just respond, and or we can also use some webhooks and something to actually let the front end know when the execution was done. So we have, I guess, all the possible implementations that you can imagine in this case, but what we aim for is not to have like sync chains in our architecture.
Cool. Good answer. Questions? Yes, one on the front line.
Hey, you mentioned that polling for transaction statuses doesn't scale. Any particular reason the reads are meant to scale unlike writes? You're just reading that the state is the same, it should scale really well, regardless how many readers you have.
Yes, but so in this transactional outbox case, the message relay is meant to delete the published messages from this table. So I guess that doesn't scale quite well is the deletes in large scale. Yeah, that's what I kind of meant.
All right, so it's the updating the table, not the polling it. Okay, that
Yeah.
makes sense.
More questions from the audience? Yes, there is one. There is two.
Hello. You mentioned sending events a lot and with this outbox. What do you put into the events? Only immutable data or also mutable? How do you deal with still like getting out of sync with different queues and maybe still API calls?
Could you repeat your first part of the question?
So what you put into the events, like if you put latest state that was just updated, if the consumer needs to combine it with other events on different entities, it can get out of sync. So how do you solve it?
Yeah. So we do struggle with this at the moment in my team. But what I don't know whether there's a kind of very scalable approach here. I'm sure there is, but what we tried here is to have very large join windows to try to reconcile events in different queues. But we do have compacted queues where these events are compacted into a single message. So rather than there's a new message published with the whole history of the state changes for an entity. So in this case, it's easier to kind of join these events with each other in different queues. Rather than waiting for each of the state changes one by one, you actually have in one single event all the history of one entity.
There was another question on the side there. Yes?
So I wanted to ask, like, when some service wants to do a transaction and there's like dependent downstream services, I understood that it has to like wait for this event that everything is okay. The downstream service is committed. Now I can commit my transaction, but it's still not atomic. Like it's still there are some like places where its data is inconsistent. So how do you deal with those?
So it's eventually consistent. And I think in a microservice architecture, this is something you accept, that your data, your view of the data is eventually consistent. Like there is some delay in the rollback and how these events get propagated across services.
Cool. We have time for one more question in the front row there. In the front row, there was one question. Yes.
Hi, thank you for this presentation. It was very insightful and interesting. You mentioned that nowadays it's an instant time to spin up new services. I'm just curious what happens under the hood. So, I don't know, you select your databases and your CI/CD pipelines and IAC, everything is done, or what actually happens in an instant setup?
Yeah. So from the developer point of view, you basically need to you need to create a PR with a configuration file where you specify your service configuration, and then that's all you need to do from a developer point of view. Once that's merged, then everything else happens in the background. But this doesn't create your service business logic, of course. So first, we have service templates for the business logic, which gives you a very thorough template, including a lot of things that are already in this service template. So you just need to focus on the actual business logic that you need to implement. So CI/CD and things like that is already taken care of in this template. And then there's the other side of actually spinning up the service, the infrastructure for your service. And that is a configuration file that when it gets merged in the background, it will get provisioned. So you just it's already deployed for you there, and you can see it then in a UI and manage it through the UI as a developer. And then you can already deploy new image versions as you update your application.
Do you have a